everyone, welcome back. This is lesson 7.5, exponential and logarithmic equations and inequalities. The objectives for today: by the end of the lesson, you'll be able to solve exponential and logarithmic equations and equalities. You'll also be able to solve problems involving exponential and logarithmic equations. Your vocabulary for today is exponential equation and logarithmic equation. Okay, so as a quick warm-up, I'd like to just go through a few problems and remind you about what we know about logs. In this first problem where it says to solve for x, we can remember our scorpion, and we can see that 16 to the 3/2 power is going to equal x. So I'm just going to do that up here. 16 to the 3/2 is going to equal x. Now, I don't really know 16 times to the 3/2 power, but I do know that 16 to the 1/2 to the 3rd power, I can do that, okay, because this power rule tells me I just multiply my exponents together, so that would be 3/2. So that is going to actually equal 16 to the 1/2 power is the same as the square root of 16, which equals 4. All right, and then we have to cube that. So 4 times 4 times 4 is 64. So there's your first answer. Again, on this problem, we're going to say x to the 3rd power equals 1.331. So let's look at how we would do that. X to the 3rd power equals 1.331. So all you would need to do is just cube both sides now to solve that, and we would see, you could put that in your calculator, but be sure and put in it as a cube, not a square, and your answer would be 1.1. And then finally, we can look at this last one, and remember, if there's not a base written in there, we know that there's an understood 10. So again, this is going to be 10 to the x power equals 10,000. So it's going to be 10 to the x power equals 10,000. And you should just be able to know that in your head, that that's going to be a 4. 10 which is going to be a 1 with 4 zeros behind it. So 10 to the 4th power. An exponential equation is an equation containing one or more expressions that have a variable as an exponent. To solve exponential equations, first you might try writing them so that the bases are all the same. So if we can see that b to the x power equals b to the y power, then we know that x must equal y. So, and that's assuming that b is not equal to 0 and b is not equal to 1. Another thing that we could do is take the logarithm of both sides, and we'll see how that works in a minute. But if we have a equals b, then we know that log of a is equal to log of b. Again, a is greater than 0 and b is greater than 0. Here's a helpful hint. When you use a rounded number in a check, the result will not be exact, but it should be reasonable. Here's example 1a, solving exponential equations. When we first look at this problem, it looks pretty daunting. We could see 9 to the 8 minus x is equal to 27 to the x minus 3, and how in the world are we ever going to solve for x? But what we do see is I see this 9 and 27, and both of those are divisible by 3. In fact, 9 is 3 squared, and 27 is 3 to the 3rd power. So let's take a look at how that would be written. Okay, so we see instead of writing 9, I just wrote 3 squared. And instead of writing 27, I just wrote 3 to the 3rd power. They're the same number. Once we've done that, to raise a power to a power, we can multiply our exponents. So here I have 8 minus x times 2. So I just distribute my 2 to both of them, and I get 16 minus 2x. Again, on this side, if I just multiply my 3 to both of those pieces, I get 3x minus 9. So now I have the exact same base, and all that I have that's different are my exponents. So I know that these two exponents have to be the exact same. So in order to do that, all I have to do now is set these two equal to each other. 16 minus 2x equals 3x minus 9. Because the bases are the same, we can just set the exponents equal to each other. And now we just have to use our basic algebra to solve this. And when you do, you end up with x equals 5. I'm sure you could do that on your own. All right. You can also check once you have solved this, and in this case we knew that x was 5. So 8 minus 5 was 3. 9 to the third power is 729. Again, x was 5, so 5 minus 3 is 2. 27 squared is 729. So you know you did the problem correctly. All right, this example is a problem that you've probably never solved a problem like this before, and it's going to be a new way. So when we look at this, I see 4 to the x minus 1 power equals 5, and the first thing I notice is that 5 is not a power of 4. So we're going to take the log of both sides to solve this. And what that means is I'm just going to multiply log onto both sides, okay? And remember, it's okay to do that. If I do something to one number, as long as I do it to the other side of the equation, then it keeps my equation balanced. All right, so if I multiply log by both sides, now I'm going to treat that log 4. Before I do that, I need to get rid of this, and I have a power rule that says I could take my exponent and just stick it out here. All right, and so that's called the power property of logarithms, and when we do that, we see that I have x minus 1 times log 4 equals log 5. Now, just as if this were a variable, I can actually divide log 4 on this side, and if I divide log 4 on this side, I need to divide by log 4 on this side. All right, so now my log 4 over log 4 is the same as 1, so it just goes away. So now what I have when I divide both sides by log 4, I end up with x minus 1 equals log 5 over log 4. Now, all you have to do is put that in your calculator. Just put in log 5, divide, and then log 4, and then you will end up with approximately 2.161. All right, so then we just need to remember to add our plus 1 onto both sides. It was a minus 1. Add plus 1 to both sides, and there's your answer. So you can also use a calculator to check this. So you just put it into your calculator to your original problem. So we would say 4 raised to the 2.161 minus 1 power, and that would get me close to 5. Now notice it says to get me 5, but since I'm rounding a little bit, it's not quite exactly 5.0000, but it's very close, and so that would be counted as a good check. All right, once you try this one on your own, turn your video off and give it a try. Okay, I hope you found this one to not be too challenging. I hope the first thing you notice that 3 and 27 both can be written as a base and an exponent, a base of 3 with an exponent. Okay, so it would be 3 to the 2 power is equal to 3 to the 3 power. So now notice that my bases are the same. So what does that tell me about these two pieces right here? They also are going to be equal to each other. So we could just set 2x equals 3 and then solve for x. Pretty simple. X equals 1.5. Again, you can check it by putting it into your calculator. 3 times 3 raised to the power of 2 times 1.5 is the same as 3 to the third power, which is 27, and 27 is equal to 27. So your solution is 1.5. All right, so turn your video off and try this one on your own again too. All right, so you should have noticed on this one, it's a little bit more challenging. The first thing you may have noticed is that 21 is not a power of 7. So we're going to need to take the log of both sides. So that just means multiply log on one side, and if you multiply log on the other, you keep your equation equal. All right, so the next thing we know is this power rule. So I have 7 to the negative x power, but I can write it like this. I can go ahead and move it to the side there. So I'm going to apply the power property of logarithms, and now I have negative x times log 7 equals log 21. Now ultimately, since it tells me that I want to solve, my goal is to get x equals something. So just like we did in other algebra problems, if we divide both sides by log of 7, This will cancel out to 1, and that will just leave us with negative x equals log 21 over log 7. Now, it's tempting to say that that would equal to log 3, but it does not, okay? It does not. You have to actually put it in your calculator, log 21 divided by log 7. And when you do that, you end up with negative x equals negative 1 point, actually positive 1.565, and then when we multiply by our negative 1 on both sides, we end up with x is approximately 1.565 negative. All right, so when we put it in our calculator, notice again it equals 21, but not exactly 21, but that's okay. It's pretty close to what we wanted. All right, so that's our solution. All right, here's another one for you to try, doing the log one more time. So turn your video off and try this one. Again, when I look at it, at first glance, I can see that I can't really set the bases equal to the same thing. So my best bet is going to be just multiply both sides by log. So when I do that, I end up with this, and now I need to remember my power rule. My power property says I can move that 3x over here. Apply the power property of logarithms. There you go. Once again, if I just divide both sides by log 2, because remember, I want to solve for x. And once again, I can't take 15 divided by 2. I have to do each of the logs separately. So I'm going to put in your calculator, log 15 divided by log 2 is going to equal 3x. And then when we divide that, whatever the answer is, by 3, we end up with x equals 1.302. All right, and when we go back and check, you get to 14.99. Ours said 15, and that's pretty close, so that's good enough. All right, here's a word problem example. It says, suppose a bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million? All right, so at hour 0, there is one bacterium because it says suppose a bacteria. So there's one bacterium, or 2 to the 0 power bacteria. Because remember, 2 to the 0 power equals 1. At 1 hour, there are 2 bacteria because it doubles in size. So that tells us at 2 to the 1 power, when the time has been 1 hour, 2 to the first power is equal to 2, and that sure enough did double, and so on. So at hour n, there will be 2 to the n bacteria. So in order to write this out, we're going to write an equation to solve it, because the question says, how many hours will it take for the number of bacteria to exceed? That means we want it to be greater than, and I went ahead and wrote it in 10 to the 6th power. Okay, so as long as we're using powers here. All right, so we're going to write 2 to the n power is greater than 10 to the 6th power. So what do we need to do to solve that? Well, I don't see that I could set them as the same base, but I can go ahead and multiply both of them by log. All right, and on the next slide, I'm going to show you we can use our power property again on both of these, okay? So we're going to have n times log 2 is greater than 6 times log 10. All right, so here's our equation as we've written it so far. Actually, I didn't go ahead and move this 6 over because I want to show you something else that's kind of interesting. Remember, this is a log base 10 because there's nothing there to tell us anything different. So we know it's a log base 10, and we had a rule. It was called the inverse property, and notice what the inverse property says. When you have a log, the base and the other number are the exact same, then the whole answer is just whatever your exponent is. So all of this can just go away. The log 10 to the 6th power is equal to 6. All right, so now we can look at our new equation. It says n times log 2 is greater than 6. So I hope you can kind of understand what we did there. All right, so next, all we have to do to solve this next is we're going to divide both sides by log 2. So we're going to take log 2, divide by log 2. So you just put that in your calculator. This is going to go away, so we'll have n equals 6 over log 2. Putting that in your calculator, we find that n is greater than 6 over 0.301. And so we could just round up to the next whole number when you multiply it out. So n is approximately 19.94. All right, so that tells us it'll take us about 20 hours for the number of bacteria to exceed 1 million. And of course, we can always go back and check to make sure that your answer is correct. In 20 hours, there'll be 2 to the 20 bacteria. And if you put that in your calculator, 2 to the 20th power, we equal 1,048,576. So that is a little bit above 1 million. Here's one for you to try on your own. Turn the video off for just a minute and give it a try. All right, so the problem says you receive 1 penny on the first day and then triple that, 3 cents, on the second day, and so on for a month. On what day would you receive at least $1 million? So the first thing we want to think about is $1 million is 100 million cents. $1 million is the same as 100 million cents, okay? So that's important to remember. And then on day 1, you would receive 1 cent. So we're going to say 3 to the 0 power equals 1 cent. But remember that 0 power is actually day 1. All right. On day 2, which is going to be 3 to the first power, we would receive 3 cents. All right. And that's actually day 2. All right. Even though we have a 1 up here on day 2. On day 3, we would actually say that's 3 squared, which would be 9. All right, so I want you to see what's happening here. I'm actually, each day is actually n minus 1. Okay, so day 3 would actually be up here, n, which is 3 minus 1, which would be a 2. Okay, so n minus 1 is actually what we're going to be using for our exponent there. All right, so once we know that, we could go ahead and write this 100 million in scientific annotation, which is 10 to the 8th power. And if you're not sure, it's 10 with 8 zeros behind it, 3, 6, 7, 8. All right, and now all we have to do is solve this. Not so hard. Take the log of both sides. And next we can use our power property. I'm going to let you go ahead and I'm going to turn the slide here so we have enough room. But notice it's log 3 to the n minus 1 is greater than log 10 to the 8th power. So all I did is just multiplied log on both sides. All right, so let's continue. Notice that I used the power log and I moved my n minus 1 over here. But I didn't do anything on this side because remember our rule, if I have a base 10, I'm actually going to just end up equaling 8. So log base 10, 10, the answer is going to be 8. So if you have the same number here and here, your answer is just 8. All right, so now again, if we wanted to solve for n, if we just divide both sides by log over log 3, and then it's going to be pretty easy. Just add plus 1 to both sides and put it through your calculator, and you end up with n equals 17.8. And the question said, what day would you receive more than $1 million? And so day 17.8, so it would have to be rounded up to the next whole number. So beginning on day 18, you would receive more than $1 million. Sounds like a good deal to me. All right, you can also check your answer to make sure. So on day 18, you would receive 3 to the 18 minus 1, which is 3 to the 17th power. And if you put that in your calculator, you see you get 129,140,163 cents, or $1.29 million. All right, a logarithmic equation is an equation with a logarithmic expression that contains a variable. You can solve logarithmic equations by using the properties of logarithms. So, for example, if I have log base b times x equals log base b of y, then I know that x is going to equal to y because this is the same thing multiplied by both of them. All right, so our equation is balanced. Remember to review the properties of logarithms from chapter 7.4. And I've written them down here for you. So if you want to write these down or take a picture of it or whatever you want to, this is a really important page for you to remember because you're going to need it a lot. They're pretty easy once you get doing them. You won't forget them. I will not let you take them on the test. You're going to have them memorized for your test. All right, here's an example of a problem that you are going to need to pay close attention to, as it's kind of tricky. So the first thing that let's do is remember the inverse property. All right, and this one was a little bit challenging to remember, so let's kind of go over it. If I have a base b and it's raised to log base b, then my answer is just going to be the x. The whole thing is equal to whatever that x is. All right, so looking at this problem, if I were to change this to where I have a base of 6 with a log 6, I know that that whole thing is just going to equal 2x minus 1. Now, if I make this side a base, I have to do the same thing on my other side to keep my equation equal. And also now I can still see if I have the same base, then I know that log base 6, 2x minus 1 equals -1. I know those two, the exponents are equal also. Okay, so now using this little inverse rule, now that I have 6 to the exponent of log base 6, then all of that is really just going to equal 2x minus 1. So I'm going to use 6 as a base for both sides. All right, and now I can say, I can use the inverse properties to remove 6 to the log base 6. So I'm using this property. I'm going to get rid of all of this. And I end up with 2x minus 1 equals 6 to the -1 power. Remember, 6 to the -1 power means that negative doesn't mean it's minus. It means to take the reciprocal, 1 over 6. All right? And now you can use simple algebra to solve this. And we see that x equals 7 over 12. So we just added 1 to both sides, which is 6 over 6. That equals 7 over 6. And then by multiply by 1/2 on both sides, I end up with 7 over 12. Okay, we're going to solve another problem. The first thing I notice on this problem is that I have log base 4 100 minus log base 4 x plus 1 equals 1. So I actually have a property. It's called the quotient property. So whenever we see a problem, log base with the same base, and it's minus and minus, what we can do is put them together and say log base b m over n. All right, so what we're going to do is just go ahead and write it out as a quotient. So I took my m, which was 100, and divided it by the n, which is x plus 1. So I'm going to have log base 4 divided by 100, or log base 4, 100 over x plus 1 equals 1. All right, now, we used it a little while ago, the inverse property. And remember, if we had the same base to the base, then we know that answer could be x. So what if I were to go ahead and make this the base now and just have these be exponents, okay? So now if I have a base with an exponent of log to the same base, that is going to get rid of all of this and just leave me with 100 over x plus 1 equals 4 to the first power. All right, so let's go ahead and use 4 as a base for both sides, and there it is. All right, now using the inverse properties on the left side, we end up with 100 over x plus 1 equals 4. And then you could just easily solve that by multiplying both sides by x plus 1, and then you could do all the other algebra for it, and you end up with x equals 24. All right, in this problem, we're going to use the power property to solve that. And so remember, when we use our power property, it just says we can take this 4 and go ahead and move it on the outside there. So using the power property, there we have it. Now the next property that we want to use on this we just want to divide both sides by 4 to get rid of the 4, because remember our goal is to say x equals something. All right, and so once I have this set up like this, I realize that this is really just written in my format that I can actually do something with. So I know 5 squared equals x, or x equals 5 squared, and now I can easily solve for x. 5 squared is 25 equals x. Pretty simple. So here it is. By definition of a logarithm, we just have to solve it like that, and so x equals 25. Okay, in this problem, we're going to use our product property. So remember, the product property states if you have the same base, log base b of m plus log base b n, we can take that m and n and just multiply it together and take the log base b of that. So I'm going to take my x plus my x plus 1, and I'm going to multiply those together. So I end up with log base 12 x times x plus 1, and that equals 1. So going ahead and remembering the exponential form, I can go ahead and notice that my log is 12 here. So if I make a base 12 of both of these, I still have everything is equal. But now when I use my inverse property, this all goes away, and I just end up with x times x plus 1 equals 12 to the first power. Okay, so there it is. X times x plus 1 equals 12. We can distribute that through, get x squared plus x equals 12. Well, it looks like I'm going to have to go ahead and use a quadratic equation on that, or maybe not. Maybe I can just factor it out really easily. All right, so let's take the rest of the equation that we had so far, x squared plus x minus 12. And when I look at this, I recognize it as a quadratic equation. And I know that I can factor quadratic equations. So I'm going to say what two numbers multiply together to get 12, add together to get 1. And I am pretty sure that's -3 and +4. So x minus 3 times x plus 4 is our factored out equation. So there it is, and now we're going to set each of our factors equal to 0. So I can solve and say that x equals 3 or x equals -4. So it's really, really important that you go ahead and check both solutions to make sure that both of them are truly solutions, because sometimes they're not. So let's check out 3 first. Here's our first equation, and we're going to fill in 3 for x. And when I do that, I end up with log base 12 3 plus log base 12 4. And remember, when it's adding, I take my 2 m and n here and I multiply them together. I get log base 12 is 1. And this is just basic. We can look, 12 to the 1 power equals 1, and we know that's true. 12 to the first power equals 12, so that is true. So 1 equals 1. So let's try it with our 4 now. It's actually -4. So x log base 12 -4 plus log base 4 -4 plus 1 is actually equal to, not ever going to equal to 1 actually, because we can't have a negative in here. We're going to get an error when you put it in your calculator. So log 12 base 12 -4 is undefined. All right. So in the end, only one solution works, and that's going to be x equals 3. So the solution is x equals 3. Okay, try one on your own. It's a little complicated, but let's see if you can do it. All right, so hopefully you were able to do that. Let's see how to solve this one. All right, so the first thing we notice is that we have 3 equals log 8 plus 3 times log x. All right, so let's use our power property of logarithms to get going with this. So what I want to do actually is I'm going to go backwards. I'm going to take this 3 log and I'm going to bring it back to my exponent here. So I end up with log 8 plus log x to the third equals 3. Now notice that I have a plus here. So what can I do with my 8 and my x to the third when I have a plus? Well, I multiply those together, so I get log 8x to the third equals 3. So now what would we do that would work here? Well, we could use 10 as a base for both sides. So when I do that, I'm going to be able to say, okay, 10 is a base and 10 is a base. And so this is an understood 10. So when I have a base and a log to a base understood, this whole piece just goes away. And that just leaves us with 8x to the third. And then we already have 10 to the third now. So using the inverse property, we have 1,000, which is 10 to the third, equals 8x to the third. And now that's pretty easy to solve. We just divide both sides by 8. We get 125 equals x to the third. And so now we just have to cube both of these. And when I do, three numbers that multiply together to get 125 is 5 times 5 times 5. So x is going to equal 5. All right, this is another hard one, and I'd like you to really turn off the video and give it some thought and see if you can figure out using all of your properties that you've learned so far. Okay, so the first thing I see when I see this is I see a minus sign, okay? So with that minus sign, it tells me I can use that quotient property, and the quotient property says to take my x divided by the 4. All right, so now remember, my final goal is going to get x by itself. So the next thing I can do, and this is kind of the hard part to remember, is remember this is a log base 10. So if I say 2 times, I'm going to go ahead and write it out here for you, 10, and use that 10 as my new base now, and just have these as my exponents, I can set these next to each other. And notice if this is a 10 and this is a 10, these will go away, and I just end up with x over 4 equals 10 to the 0 power. Remember, 10 to anything to the 0 power is just equal to 1. So let's see what we're actually going to end up with. When you use your inverse properties, we end up with 2 times x over 4 equals 1. And now that is a really easy problem to solve. We can simply multiply both sides by 1/2, and then multiply both sides by 4. And we end up with x equals 2. All right, so watch out for calculated solutions that are not solutions of the original equation. So you need to make sure you're always checking. Okay, this example, you're going to be using your graphing calculator. So you're going to use a table and graph to solve this problem. So the first thing you'll need to do is get your graphing calculator out, and you're going to go to the Y1 or the Y equals button. And in Y1, I want you to put in 2 raised to the x plus 1 power. And then in the Y2 section, I want you to put 8,192x. So once you have those in your Y1 and Y2, the next thing you need to do is go to table. So that's going to be second table. And in the second table, you're going to find values of x values where Y1 is greater than Y2. So if you look up here at this, Y1 is greater than Y2. Well, they're the same here. Okay, so now at 17, Y1 is greater than Y2. So in the graph, find the value at the point of intersection. All right. And so we can see the solution set is all of the x's that are greater than 16, because at 16 they're equal. So all of the x's that are greater than 16 are going to satisfy this inequality. Here's another example to try. Again, on your graphing calculator, in Y1 you would graph log and then open quotes x plus 70. In Y2, I want you to write 2 log x over 3 in Y2, all right? And then again, you're going to take a look at your graph, and take a look at your table. And in the table here, we can see the x value. We're trying to find the x values where y1 equals y2 because we had up here equals. All right, so here we can see they're going to equal each other is where they intersect, okay? And so the intersection is x equals 30 and y equals 2. All right, so you can look at that at a table like this. Again, you would push on your calculator second graph to get this table up. And here, when x is 30, y1 and y2 are both equal to 2. So that's the point of intersection. All right, so your solution is x equals 30. All right, try this one on your own. Again, you're going to put 1 in y1 and 1 in y2. So turn your video off and give it a try. All right, so if you entered 2 to the x power as y1 and 4 to the x minus 1 as y2, then put it in your calculator, and we're trying to find out where they're equal. We can see at x equals 2, they are both equal to 4. All right, and you can also see it in the intersection. I prefer using just the table here. It's a lot easier to read, but you can always do the graph and then find the point of intersection. And we see that the solution is x equals 2. All right, here's another one for you to try on your own. Turn the video off and give it a try. All right, so I hope you used your graphing calculator, and at y1 you entered 2 to the x power, and y2 you entered 4 to the x minus 1. All right, in this table you can see we're looking for where the first y1 is going to be greater than y2. So we see when x is 2, they are equal. So when x is 3, y1 is less than y2, but when x is 1, y1 is greater than y2, which was 1 there. So our answer is going to be when x is less than 2, then that satisfies our equation. All right, here's another one for you to try. Turn your video off and give it a try. This one says solve log x squared equals 6. All right, so you should have been able to put in y1 log x squared and in y2 6. So now we want to know when they're equal. You can look at the graph. They're going to be equal when they intersect each other. I prefer looking at the table. You can see when they're equal is there'll be 6, 6 when they'll be equal when x equals 1,000. All right, so here's a lesson quiz. If you'd like to turn your video off and give these a try to see how much you learned on this. I know this was a lot of information for you, so if you'd like to check it and see how you're doing, that's a great time to do it. Okay, here's the answers for the part 1 of your lesson quiz. All right, and here's another part of a lesson quiz. You can check yourself to see how you did with that. Again, these are just a lot of problems, and the more you do, the more comfortable you'll get with them. Okay, so I hope you were able to turn your video off and give it a try, and here are your answers. 70 minutes, and the last one is x is going to be approximately 0.903. All right, well, that's the end of our lesson for today. I hope you learned a lot, and you may need to go back and re-listen to this video one more time if you're not real clear on it. Okay, you guys have a great day. See you soon. Bye.